what I'm hoping to do really is just give a quick overview of what's going on in quantum computing. One of the things I've come to understand that this sector, perhaps more than any other, has a lot of interesting opportunities and challenges for a wide number of users, but there seems to be a significant amount of confusion in terms of what quantum can offer and really what its place is in the advanced computing sector. So I'm going to try to lay some groundwork that hopefully will clear up some concerns or questions, and also give you a sense of how we see quantum computing going forward as part of the overall advanced computing sector. Just a quick outline. This isn't a commercial as much as it is an explanation about where we come from. Now, Hyperion has a long history of looking at high performance computing, which is, we tend to think of it as the pointy end of the spear when it comes to computing. It's where, in essence, performance is far more important than price performance. And I'll give you some examples of what that means in a few seconds. But the bottom line is, what we really like to look at is advanced computing, the overall spectrum of computing technologies that really drive performance, new applications, and the ability to really advance science and engineering problems through the use of computing technology. And about 5 or 6 years ago, we started getting a number of questions from our clients who not only build and supply HPCs, but from our customers who use them in their workloads. And they started saying, well, we're hearing a lot about quantum, and we want to know how this is going to really affect our overall workload environment. How should we be thinking about bringing quantum into our computing environment? And at the time, we were really looking at quantum as an issue of how is this going to affect the HPC sector, the high performance computing sector, the places where most of the work is being run on expensive machines, performance is king, and science and engineering is the workload of the day. Well, what we found since we started doing this is that the enterprise IT world, and in essence, users that heretofore were not companies that were rethinking about HPC, but saw quantum as an opportunity to bring in an interesting computational capability that could give them a certain amount of competitive advantage. And we've started to see an awful lot of interest within that enterprise IT sector, non-HPC users who are very interested in quantum and some of the opportunities this brings. So really, this is not just the pointy end of the spear in some sense. It's something that has applicability not only within the HPC environment, but also within enterprise IT writ large. Well, I promised that I would talk about advanced computing and quantum's place in it. So let me just give you a quick look at the advanced computing sector as we look at it at Hyperion. Right now, we look at the technical computing market being worth about $24 billion in 2020. And as I said earlier, technical computing here are systems that basically use about 50% or more of their performance cycles to do science and engineering applications. That means you could be looking at a $20,000 workstation that sits serving a single researcher in a lab, all the way up to some of the largest HPCs in the world. And that can cost an awful lot of money. For example, right now, the fastest high-performance computer in the world it's called the Fugaku system. It's installed at a Japanese government research facility in Japan. And its peak performance is 513 petaflops. And that means that basically every second it can do 513 times 10 to the 15th floating point operations. And that's every second of every minute of every hour of every day. It basically cost over $1.1 billion to build, and it uses the same amount of electricity in an area about the size of 2 tennis courts that is used by about 20,000 residential homes here in the United States. So it's about a 25 megawatt system. Very advanced. It took about 6 or 7 years to build, and that machine will be operational for perhaps the next 8 to 10 years. Now, we in the scientific computing world like groups of threes. So that's why we talked about 10 to the 15th as petaflops. That peta is the prefix that tells me 10 to the 15th. The next big milestone is exaflops, 10 to the 18th. And we're basically on the verge of moving into what people are calling the exascale realm. And there are a number of new exascale systems that are out there being researched and being built right now in the United States, in the EU, in Japan, and in China. And we're starting to see those rolling out the next few years. The 3 US systems that are on schedule to be delivered next year and the year beyond at 3 large government Department of Energy facilities are each on the docket for a cost of about $600 million apiece. That doesn't include operating costs. If you're running 25 megawatts per system, you could be looking at multiple millions of dollars of heating and cooling and electric costs per year. And these things generally require $100 to $200 million buildings to keep them happy. So these are expensive operations, but this is what it takes right now in what we call the classical world, the traditional computing world. So where does quantum fit into all this? How does it fit into multiple $100 million HPCs that are capable of 10 to the 18th kinds of operations? Well, if we stand back from a second, I can tell you that right now the promise of quantum computing is substantial. These quantum computing systems have the potential to exceed the performance of these conventional computers for specific problems that have real important use cases for business and basically mankind in general. In things like physical simulation, the ability to simulate complex physical actions that can give great insights into things like material science, chemistry, pharmaceuticals, and oil and gas. There's great capabilities in machine learning. Artificial intelligence driven by quantum computing promises to bring new insights into the growing field of artificial intelligence. And the big one right now is optimization, the ability to think about how to do something better and faster in a way that is virtually impossible to do on a traditional system. A simple example would be an airplane pulls into a gate at an airport. It has to turn around in 30 minutes. They have photographed every piece of luggage that's going to go on that plane. How can you organize that luggage to be loaded in effectively, quickly, and take optimal use of the space while making sure that the plane is properly balanced so it can take off safely? That's a very complicated problem and something that classical computers, once you get beyond more than a few pieces of luggage, simply can't handle. That's a typical application or an interesting application for quantum computing and something that commercial vendors like Airbus are looking at as we speak. Ultimately, the goal for quantum is to come up with this concept of quantum supremacy. Are there applications out there that are literally not possible to be done on a classical computer that can only be done on a quantum system? And that is one of the long-term goals, but not one of the short-term goals. And I'll discuss that a little bit, but I want to give you a quick example of what quantum supremacy at its finest looks like. And here we're going to talk about the exemplar of quantum computing. And basically, the bottom line here is what we're looking at is an algorithm that does something relatively mundane at first principles. It's factoring a number into its prime multipliers. So basically, the number 15 can be broken down into 5 and times 3, where both the 5 and 3 are prime numbers. They can't be broken down any further. Well, in 1995, a researcher named Peter Shor came up with an algorithm on a quantum system that offered the following kinds of details. If you look at the graph on the left, you'll see that at the bottom where it says number of bits, and you'll see, say, 1,000 bits. And if you follow 1,000 bits up, you'll see that the ability of a classical computer to factor a 1,000-bit number takes about a year and change to do, where that line intersects. That means that basically, if you've got a 1,000-bit prime number, the product of two primes, it takes you about a year to figure out what the factoring is. Now, that in and of itself isn't very interesting, but the issue there is that this particular factoring algorithm is the main determinant in basically almost all of the encryption technologies used today in both national security and finance and all sorts of other applications to keep communications secure. The inability of classical computers to quickly factor numbers is one of the main reasons why it's integral in most of the encryption schemes out there. And as you can see, if someone says, well, factoring 1,000 bits only takes a year, I'd like much more security, or computers get faster, what do we do in that case? Well, if you move over to, say, 2,000 bits, you'll see that curve goes up, and now it takes 1,000 years to do. And if you go to 3,000 bits, you're at 1 billion years to factor it. So it grows very quickly in the classical world. But look at those rather gentle, slightly upward sloping lines that are derived off of Shor's algorithm. You can see here that when you have 1,000 bits, it only takes a couple seconds on a quantum computer. And if you go to 10,000 bits, you're still at an hour. So there you have the example of potential quantum speed up on an algorithm. And this kind of algorithm generated significant enthusiasm, not only for the fact that it demonstrated that there were things that quantum could do that no other classical system could do, but also that had an interesting and compelling real world application. Um, that generated most of the enthusiasm. The quick spoiler alert here, unfortunately, is that the flow of algorithms that follow Shor's has been very sparse. It's been very difficult to identify algorithms that have this kind of marked and dramatic performance difference between classical and quantum, but the search goes on. I can go quickly over what makes quantum computing different in some sense, and there's really two phenomena that make all the difference in the world. The first one is superposition, and what this really says is that a qubit, the quantum equivalent of a binary digit or a bit, doesn't just have a value of 1 or 0, but can it exist in both states at the same time, enabling simultaneous computation on both branches of the bit. And if you start to think about how if I have 2 or 4 or 10 or 100 qubits, now I have significant simultaneous computational capabilities that far outreaches what I would get in a traditional binary 1 and 0 implementation. The other thing is entanglement, the ability that qubits can share their state with neighbors that they are entangled with. So if something happens to one particular qubit, the implications on what happens at an entangled qubit with it are related, and quantum algorithms can take advantage of that phenomena. Those are two wonderful phenomena of the quantum world. The problem is they are very difficult to establish and maintain, and that's really some of the main complexity with developing quantum computers today. The difficulty of establishing qubits to maintain superposition and entanglement to stay in their quantum state is very difficult. It sometimes requires severe requirements for material production, temperature, all sorts of conditions where if they're not maintained properly, you drop out of quantum, and what you have is a very interesting and very expensive binary 1 and 0. I just want to give you a little flavor of the complexity. The chart there on the top left shows you a binary digit, a bit, which has a choice of 1 and 0. The block sphere, that circle on the right, gives you a sense of what a qubit can be thought of as. It's basically a sphere where you can have a variable exist literally anywhere on the surface of that sphere. And if you're, say, on the x-axis, if you will, the equator, what that means is you are now dealing with a qubit that is either a 1 or a 0, and you can process it that way. The interesting thing here is that it's not easy to manipulate these qubits. There's lots and lots of interesting error rates going on, and I just given a simple example here where I take a classical input of 0, 0, 0, I run it into my quantum processor. All sorts of quantum goodness takes place using advanced algorithms like superposition and entanglement, and say Shor's algorithm or other algorithms like Grover's or something. And then I get an output. Well, because the process is noisy, and I talked about the difficulties of maintaining the superposition and entanglement, what you get out sometimes is not as precise as what we're used to in the classical world. And so the output of a rather simple operation, and really all I did with this particular example is for those 3 digits that go in 0, 0, 0, I did nothing to the first one. I did a inverse of the 0 of the middle one, 0 to 1, and then I did 2 inverses of the last one, from a 0 to 1 and then 1 to a 0. And so you can see the output about 90% of the time was 0, 1, 0, the correct answer. But to get this distribution, I basically had to run this experiment over 8,000 times to produce a histogram of results. And so basically what that means is I've done a very simple calculation and I get the right answer about 90% of the time. So imagine how that would scale if you're doing a much more complex operation. That's really the hard part of quantum, is the noise and the imprecision that is inherent in quantum computing that makes it difficult to translate from this classical world where we're used to high degrees of precision to the quantum world where we have all sorts of quantum goodness, but we have to deal with issues of noise and other complexities. So as it shows here, there are some substantial challenges ahead in bringing quantum to become basically a nice, stable commercial product. The uncertain performance gains I talked about, algorithm development, replicating the kinds of performance gains that we see in Shor's algorithm. Timeframes. This is not an engineering solution yet. In essence, we haven't even figured out exactly what the best way to build a qubit is. There are many different ways, superconducting qubits that live at millikelvin levels, that basically very small increments above absolute zero. We have photon implementations. We have things called trapped ions. We haven't even begun to think about which is the best way to actually build qubits. So there's lots of uncertainty there. I just want to give you a sense of quantum research activities from 50,000 meters, just to give you a sense of what's really going on in the world in quantum research. And all this chart, these two charts really try to show, we'll concentrate on the one on the left. This is basically a count of research publications over the last 5 years by country, basically that come out of quantum computing research. And the three things that I want to point out is one, is that in every country that we look at that's a major developer at this point, the trend is upward in the last 5 years. Two, China and the United States are leading in the development of this. And three, there's an awful lot of countries out there who are doing quantum computing research. This is not limited to a single nation. And this is not something where there is anybody who has an inherent lead. There's no legacy in quantum. Everyone started from the same level playing field a few years ago. What that means is right now, because there isn't a significant market for quantum, they're being driven primarily by government programs. And we see here a select range of quantum computing programs. And, to be sure, it's not as if Canada has one program and this is it. This is just an example of a Canadian program. Same within China and the EU. There are EU programs that transcend the EU nations writ large, as well as individual programs going on in France and Germany. The key here, the point of here is that this is a widespread government-sponsored research technology at this particular point in time with a lot of interest around the world. I just want to give you a quick snapshot of the commercial landscape. And forgive me if this is US centric, I am within the US, and I do try to remind our clients that this is an international phenomenon, and thinking about this only as US is going to doom you to failure. But we'll talk a little bit about some of the foreign activity in a minute, but this unfortunately is primarily US based. The key here is that there are a wide range of hardware suppliers out there, and they have greatly different compositions. We have large companies like IBM and the EU-centric Atos as suppliers of quantum technology. Honeywell, a large vertically integrated company that has dips its toe into aerospace and advanced manufacturing, recently came out of a 10-year stealth mode to announce their participation in quantum computing. We have an awful lot of new entrants into here. I call these pure play companies. And these are folks that live not only through the funding of government programs, but also through venture capital. The idea that the VC community, the folks that fund new technologies in hopes of realizing 20 to 40 paybacks in 3 to 5 years, have put money into a lot of these companies. And there's an awful lot of them. Intel is a great player in this. And we have some non-traditional players, Alibaba, AWS, Baidu, Google, and Microsoft. And there are myriad stealth players out there, folks that I'll get calls from who want to know a little bit more about how the market's progressing, but no one's ever heard of them. And they may sometimes appear and sometimes they just go away. So I hope someone out there at least is scratching their head and saying, Google, Microsoft, and AWS cloud service providers are involved in this? And the answer is yes. And each of them have a significant and broad range of quantum computing services, if you will. For example, Amazon with their Bracket program, they provide access through the internet to some of the quantum computing hardware suppliers like Rigetti, IonQ, and D-Wave. So I can sit down on AWS and within 15 minutes be running some simple code on a Rigetti quantum computer and being charged by Amazon the same way if I was just running a simple image to run some software or access it as a software as a service platform. Same with Google, same with Microsoft. What's happening here is the cloud service providers are very interested in trying to come up with some way to differentiate themselves from their competitors, and they view quantum as an opportunity to do that, something we're watching very carefully. We can talk about the number of software companies out there, and these are just a sample of what's going on in the US. And there's a lot of companies going on here, but what I think is interesting about this chart is the idea that it is possible right now, because of the way the stack is running in quantum computing, the hardware and the software stack, there's enough definition and separation between hardware and software where even a small company can come up with quantum applications that can run on machines from different vendors. And remember, I said earlier, there's some very different modalities, the way the qubits are constructed, and yet because of the sophistication of the software stack, I can write a piece of software that runs on a Rigetti machine, that runs on an IBM machine, that runs on a D-Wave machine, or something that maybe Google's thinking about. I didn't go into too much detail, but Google's working on some of their own hardware as well. So the point of this is lots of small companies, lots of interesting developments, but at the same time, they don't have to pick a winner or loser yet when it comes to quantum hardware. I just wanted to point out here that European participation is high. This is just a samples of some of the startups that we've been tracking in the last few years. Barriers to entry to enter quantum computing right now are pretty optimistic. You can get funding. You can, if you have an interesting idea or an innovative thought process, you can probably get some funding to stand up some work. It's not like many of these companies will be around long term, but certainly there's a vitality in the sector that I think can be appreciated. Interesting work going on in Japan. I won't go into too much detail, but the key here is these are the major IT suppliers in Japan, and they're all taking a different perspective on looking at how they can access some particular portion of the quantum market. The one I'll call out just because I find it an interesting example, NEC, a large Japanese HPC maker, has basically joined forces with a US company called D-Wave, and they're trying to come up with hybrid algorithms. Basically, the idea that instead of having a pure quantum algorithm or a pure classical algorithm, can they come up with algorithms that do both at the same time? You basically iterate between the classical system and the quantum system to basically take advantage of the particular performance capabilities of each to complete a single job. This is an interesting way to avoid some of the complexities I talked about earlier with noise and the issues of maintaining entanglement and superposition by making sure that only quantum access capability is used when necessary and everything else is done on a classical system in a much more traditional and controlled environment. Hybrid classical quantum computing is, I think, a really interesting interim solution for a lot of the companies, and we're watching this with a no small degree of interest. We've been asked by a number of folks to try to figure out exactly how much this market will be worth in the next few years. So what we did is we turned to surveys. We talked to, in this case, we just completed one a few months ago where we talked to 135 different suppliers of quantum computing technology. Unfortunately, it was primarily limited to the US, but we tried to reach out to a wide base of academic, commercial, and government users. And this is just a quick spoiler alert from the results of those surveys and using some other metrics. We decided the Hyperion forecast that the global quantum computing market was worth about $250 million in 2019, and we're anticipating a compound aggregate growth rate of about 27% for the next 4 years, meaning that the market grows to about $830 million in 2024. You can see that compared to the HPC sector, this is a relatively small number, but we're pretty happy with this. And we talked to a number of folks in the sector after we came out with this, and this seems to be a relatively conservative middle of the road estimate. The key here is that it shows growth potential. And what that is important is because that means that those venture capital folks and some of the governments who are interested in funding this can start to see return on investment and the emergence of a viable market. And nothing ensures success like success. And so we're very happy to say that this prediction or this forecast was something that at least demonstrates a growth in the market. Some of these other details here we can talk about at some other point, but the bottom line here is essentially that the market looks like it's going to be around at least for the next few years. This is just a quick snapshot of, and this is what people who do market research like to see. We basically divided up the market by major segments based on some of the surveys we did, and this shows you how the markets are going to grow and segment out in the next 4 years between the sale of quantum hardware and software access through cloud models, through those CSPs we talked about earlier, markets for software in terms of application and middleware. And this is just a way to establish a certain amount of segmentation within the market, again, developed through conversations and surveys with major suppliers. In addition to talking to suppliers, we also wanted to talk to buyers, users, and find out what's going on out there. So here we talked to about 115 different users. And here we were able to move out a little bit into the EU, which I was quite happy about. I would have liked to see more in Asia Pacific, but at least we got out of the United States. And some of the interesting things we found was basically we asked them about what are your, as users of people who are either using quantum today or thinking about using it in the next few years, what are some of your expectations? And what I liked here is that they're broad. It wasn't quantum supremacy. It wasn't, if I don't have an application that I can't do on classical, I'm not interested. It was, are you going to enable new applications? Are you going to speed up my existing applications? Are you going to develop new ones? There's a broad range of expectations here that are very amenable to what we see in the quantum technology field. So it's not as if the users have some very specific expectations that if they're not met, they're going to walk away from quantum. And we found that very encouraging. We asked them how much performance. We talked about that, 1 hour versus a billion year kind of Shor's algorithm performance. But users right now are basically saying, if you give us 50x performance computing on a quantum system, we'd be perfectly happy with that. That gives us a competitive advantage of 3 to 4 years, perhaps, over our competitors. So they're thinking of quantum computing as an accelerator, if you will, something that puts it more in the line of a GPU accelerator as opposed to a standalone quantum environment. So this is, again, a very encouraging thing. And this is where we got that 27% CAGR. When we asked all these companies, what's your budgets for the next few years in quantum computing? And what we saw was that a lot of companies that have quantum now have aggressive plans to grow their budgets for quantum. A lot of companies that are thinking about the sector are planning on jumping in the very near future. Again, positive outlook for the sector. So really what this ultimately means is, how is all this going to play out in the near term? And I know I got about 2 minutes to go, so I always like to put a chart that I can either skip through or spend a long time on. So since I have 2 minutes, I'll just jump quickly through this. So the near-term quantum computing ramp up here. There's many applications and use cases being explored out there. I mentioned earlier the Airbus phenomena of loading a plane. Some of the other optimization algorithms that are out there are best ways to the classic traveling salesman problem. What's a good example? Volkswagen did a study where they did real-time mapping of traffic flows between airports and the major city centers. Because when you do Google Maps and it gives you an alternate route because of traffic, everybody gets the same alternate route. And that means that within minutes, that alternate route is now a major choke point. What Volkswagen was looking at is, how can you route every car on the road to minimize the average travel time of every car, not just sending everyone off to one route. So optimization is a really interesting one. The key here, though, is trying to build bridges between quantum computing expertise and subject matter experts. If you walk into an oil and gas company today and say, so what are you guys thinking about quantum? The answer is, I don't know. We don't have quantum experts on staff. We don't know how to bring quantum into our existing compute environment. The people that can bridge that gap are going to be one of the most important and critical elements in quantum. And we're really trying to track to see how that particular QC subject matter expert sector emerges. The key that I want to make here, and we talked about the acceleration and some of the applications for quantums that are very specific. Quantum is not a replacement for classical computing, but a companion technology. The two will work in concert with each other. Quantum is not the end-all be-all. It has some impressive performance gains, but only for a specific narrow class of applications, similar to what we see for GPUs in traditional computing, where they work very well on some applications like artificial intelligence, but work terrible in others. Quantum has the same kind of characteristics. And the key here is that development is happening in many dimensions and in parallel, which adds to the confusion and adds to the fun of trying to keep track of this. We're seeing new opportunities in hardware all the time, breakthroughs in software, new algorithms. I mentioned hybrid classical systems, and even quantum-inspired hardware and software, where companies are saying, hey, that's interesting what the quantum world's doing, but I can do that on my classical system. I can rewrite my classical algorithm based on insights I've learned through quantum algorithms. That's also another interesting avenue that we're keeping track of. So basically, that's really what I had to say today. Again, I want to thank the folks from FTC 2020 for inviting me to speak. This is my email address. If you have any additional follow-up questions, comments, if you want to throw rocks at anything I've said here today, that's more than welcome to hear. But otherwise, I will now be quiet and throw it back to Lars.